Hi everyone, so I'm Asma FARJALLAH. I'm going to present you the Intel Xeon Phi architecture today with some focus on the energy. I hope that I'm going to answer all the questions, and please don't hesitate to stop me and ask if you have any. So the disclaimer as usual. So brief introduction. What is Kernel compared to the Intel Knight's Corner? You've already tried it, I guess. And three main differences are the bootable Xeon Phi Knight's Landing that we have compared to Xeon coprocessors. The second main difference is the increased amount of DRAM that we have on Kernel compared to KNC, and also the increased stream bandwidth that we have thanks to the MCDRAM shipped on the kernel. So these are the main differences between kernel and KNC. We have also different SKUs, different flavors of kernels. Each can have integrated fabric on it with an additional amount of power if you have fabric integrated. So we have mainly, I will use the 7210 for the upcoming slides to show you some results. So let's start with the microarchitecture. So this is the presentation. Who already did some experiments or did use kernels before? Just to know if I need to go through the slides very quickly or should I take my time? Okay, majority of the. So I will go very quickly and as I said, just stop me if you have any questions. Kernel is mainly characterized by the mesh 2D that we have. So we have cores that are connected through this 2D mesh. We have also MCDRAM that is shipped, and we have 6 MCDRAM channels, and we also 4 MCDRAM channels, sorry, and we have 6 DDR4 channels. Main characteristics also is that we have on this node we have a single socket. We don't have 2 sockets as we usually have on Xeon as we used to. We have also fabrics that can be integrated, as I said, via the Intel LAPACK technology. And we have the MCDRAM stream triad measured can be over 400 gigabytes, something like 490 gigabytes per second. VS. Is
MCDRAM like a cache?
It can be considered as a cache. It can be considered as a direct mapped cache if you choose to use it this way. But originally it's a memory, it's a multi-channel DRAM, and it's mainly used as a memory. I will come back to this. So if it's not clear, then just ask. So we have this concept called tile. A tile is an agglomeration of 2 cores with a shared L2. The cores are out of order cores, which is not the case with the Knight's Corner before. These cores have 2 VPUs each, and the L2 is 1 megabyte size. We have this CHA, the caching home agent, that is a tag that is distributed among the tiles on the mesh, and it's used for the coherency between the L2s we have around spread around the mesh. So VPU quickly per core we have 4 threads. We have also, for example, we have one important thing is the loads and stores port that we have. We have 2 64-bit loads and 1 64 for the stores. Also, we have some improvements in terms of cache lines splits and the access to these cache lines that can be aligned. It's supported. We have also the gather and scatter support via the AVX512. Then threading. Threads, they can share some resources. Among them, we have the order buffer, for example, and the reservation stations. But these can dynamically partition it, but TLB and caches, they're shared between these threads. So threads, they are used for throughput and for hiding latency, of course, and this can be very useful for some stalls that we may have in the code. For ISA, we have this AVX512 addition. So we have the foundation in common with Skylex. I don't know if you already tested, but if we just compile using the foundation, we can use the both binaries for both architectures. But we have the conflict detection, which is very useful for codes that have histograms. Also, as I said, we have these prefetching additions that supports gather and scatter. And then for mathematical codes, we have exponential and reciprocal function instructions. So to come back to the configuration of the MCDRAM, and we have 3 ways to configure it, mainly 2. But so you can consider the MCDRAM as a cache, and you set it in the BIOS to use it as so. And you can use it as an extension of your DDR, and in this case, you will have your addressable area will start with the DRAM and then continue on the MCDRAM. And in this case, you won't expose the MCDRAM unless you ask for it. Whereas on the cache mode, it's automatically done for you. So it depends which, if you are less impacted by the latency, because if you use the cache mode, you will have more latency since you are going to hit the DRAM, and in this case, we'll have slightly augmented latency. In this case, cache maybe can be important for you. If you are very limited to the bandwidth and you need a very high bandwidth, then the flat mode is maybe more suitable for you. And then you have the hybrid version, where you configure a part of your MCDRAM as a cache and the other one as an extension of your memory. And all this is done on the BIOS level. So the flat MCDRAM sees in the case of flat MCDRAM, you see your MCDRAM as a single node, NUMA node. So it's separate from your core plus DDR node, which is 0. And unless you specify it explicitly using numactl utility, for example, you will have to use it. You will have to specify it in your code. And for this, you will have to use APIs like HBM APIs. So we have memalloc and gmalloc that are accessed freely. That they're open source, and you can use them for your code. So just to illustrate, these are some of the calls that you will need. So you just replace your malloc, for example, by HBW malloc, and these will be applied for specific arrays in your code. I don't know if this answered the question. No? Okay. This is another illustration also. So it's for C and for Fortran codes. How we use the HBM, it's not important, but just code snippets. Then the mesh interconnect. So we have these, I've been talking about the CHAs and the distributed tag directory that we have on each tile. So so I've been talking about configuring memory, but we need also to configure mesh interconnect. And mesh interconnect is going to impact the way you are accessing data in the memory. So it's important also to configure it the best way in order to have the less latency and the better bandwidth that you can expect. So we have 3 ways to configure it. The first one is the alt wall configuration. It's a fallback configuration. It's the one that gives you the worst performance you can expect. And it means that you don't have any affinity between these tags that are very useful to get your data with the memory channels. So you can, if you have an L2 miss, you will have a non-optimal path around this mesh, and you will have huge latency, and you will not access your data as quickly as you wished. So this is a fallback, and it's used for debugging usually. The second one is the most common one, is the quadrant, and virtually your mesh is decomposed in 4 areas, quadrants, let's say, and it guarantees affinity between the tags and the memory channel. So it guarantees that as soon as you have your L2 mesh, you are going to have the shortest path between your directory and your memory. Core, it can be wherever on the mesh, but at least between the tags and the memory, you have this affinity. And it's the simplest one to use because you don't have to change anything on your runtime variables or on your code, and it guarantees a decent performance. The latest one, and which is theoretically the best one, because it's going to have the smallest latency with better bandwidth, is the equivalent to a 4-node socket, and it's the Sub-NUMA clustering. So you can imagine it as a 4-socket node, and you have really the smallest path you can have between your L2 mesh, your core, your directory, and your memory. Any questions? Yes?
You said that the cache mode is driven by the BIOS?
Cache, yes.
And is it also true for the cluster mode?
Yes, sure. Both of them are.
So you need to tune 2 parameters in the BIOS?
Yes, but we have, since then we had some utilities in order to be able to reconfigure using your terminal in order to reconfigure these features, but it means that it means that you need to reboot your kernel.
So you need
16
16 nodes.
nodes.
No.
We can discuss that afterwards. So I will go through the BKMs. This is really the outcome of all the work that we've been doing on kernel with some real applications. And 2 points are for me performance libraries and MPI. So for performance libraries, MKL supports kernel since the version 11.3, but we always recommend to use the latest one for better performance, of course. Since the 11.3.2, they made a lot of effort on the performance, and it's at least please use this one at least for performance. Linking, you may know this link for the best line in order to link with MKL, with Intel MKL. So very briefly, the most important thing to talk about is this MKL fast memory limit that should be set when you are in cache mode, because for flat mode and for cache mode you don't have exactly the same algorithms, and if you are in cache mode you need to set this one to 0 in order to get the best performance. The next slide will showcase more clearly. So you have the DGEM in both cases, flat and cache, and the only difference is to set this flag for the best performance. Another thing which is worth to mention is that MKL will automatically use the number of cores and the number of threads used is equal to the number of physical CPUs, and this is set automatically for you. You don't need to bother with that. So just for your information, and this is the best performance that we can get if you have MKL that you are using. Also, in terms of alignment and everything, it's of course done in the library, and we have all the alignment set by default to 64 bytes for this library. Again, this is the MKL fast memory. Another usage for MKL fast memory limit is where it can be used for the internal buffers of MKL. You can limit the usage of MCDRAM to a certain amount. In this case, for example, it's set to 1 gigabyte. And also, if you are in flat mode, you need to use the numactl-m utility to choose MCDRAM or DDR. Okay. Another thing, but this is not proper to the libraries, the allocation, huge pages. They showed that they can be very interesting for a lot of applications. So maybe you can set the huge pages and try. Also, the scalable allocators, such as TBB, can be very interesting for performance for some applications. And then MPI. So HBM Awareness have been, yes?
Does it use these transparent huge pages?
Yes. Yes. So HBM Awareness can be set for the MPI library using some functionalities. So you have these functions or the function MPI WinAlloc shared or environment variables. I'm just going to talk about the MPI HBW policy because the settings is more or less the same thing, but for the MPI HBW policy, so you are going to specify the user buffers, the MPI buffers. The user buffers are the mandatory ones. MPI buffers, and then some buffers that can be used for the MPI WinAllocate shared. So you have this key names, so this key flags. You have the preferred, the bind, and interleave. And preferred is going to allocate your memory on your MCDRAM, preferably if you don't have enough space, you are going to the MCDRAM. Bind, you are going to bind it to the MCDRAM. So if you don't have MCDRAM, it's going to have you're going to have a crash. Or then you're going to interleave between MCDRAM and your DDR. For the other settings, it's exactly the same thing. And you will have the slide, you will have all the info. In terms of policy, if you are using the functions, this is the order of priority. So you have your MPI info, then you have your MPI HBW policy, and then you have the bind win allocate. Then for MPI, if you are using multi-nodes, then you want to set your fabric usage. So for the lowest latency, we recommend to choose OFE or TMI. If you are using MPI OmniPath, it's recommended to add the MPI TMI provider, PSM2. And then for if you have your cluster and die activated, so we recommend to use the MPI pin domain set automatically equal to auto, but you may want to also use the NUMA value, and it will go to you are going to use your a particular NUMA node. Last thing is to avoid static MPI libraries and try to, when possible, try to use the dynamic libraries. Then this is a quick reminder of the OpenMP Affinity between OpenMP4 and Intel. And of course, if you have MPI plus OpenMP, you need to set your MPI pin domain. Then you are going to set your CAMP affinity and the number of threads that you are going to use. Simple. So quickly, what time is it? Quickly for the power management. So for power management, we have this technology called the enhanced Intel speedup technology that allows the monitoring of the clock speed of your CPU. So this is proprietary to Intel, and I'm going to expose some drivers that we are going to use in this case. So we have the P state. And it's exposed to the US using, if you are going to look at the CPU FREC, it's exposed to per CPU granularity, and it's platform specific. In order to control the P state, we have the MSR, we have the legacy MSRs. So we have the platform info, the perf CTL, we have status. But we also have some drivers like the Intel P state driver, and it supports kernel available since the version 3.9 and onwards. For the C states, also we have for the idle processor, we are going to have this CPU idle also for CPU granularity. We have drivers for the C states like the Intel idle, and for kernel it supports kernel starting from the 2.6 version. And finally, we have for power management, for power budget management, we have many building blocks. One of them is the RAPL, the running average power limiting, and it supports kernel since the 3.13 kernel. Now the last part is a prototype that I've used for kernel, and we've been going through the optimization for kernel. And I did some measurement for energy and for power, just to highlight the importance of optimization on the performance, on power consumption on this kind of architecture. So the code is available, so it's already online, so you can use it and optimize for kernel if you wish to use it. And I guess that many of you are familiar with this kind of code, so it's a stencil code where you have to access some values on your neighbors, and this is the first version of the code. Allocation of memory have been done in a linear fashion. There were attention paid to cache associativity, and in terms of optimization, no cache blocking was implemented for the first version. As a baseline, this is the performance that we get. So no vectorization have been seen, and we have this elapsed time of 57 seconds as reported by the tool. Just to quickly, so this roofline will show that the performance is limited by the performance of the DRAM bandwidth. We have a kernel that is in cache mode. Yes, in a cache mode. So in terms of power, we have this IPMI interface. We have a tool based on this interface that permits the measurement of the power of the whole node, of the whole system, the power of the core, and the power of the memory. So we see that we have, in terms of energy, this makes 1,300 joules. Then we did some optimizations, a lot of optimizations. And in terms of vectorization, in terms of alignment of the code, in terms of cache blocking, and we really have a smaller elapsed time with vectorization efficiency that is set to 100%. And in terms of energy, we have in terms of roofline, we move up with gigaflop per second that is higher than before, and energy also is way slower than before. We have 1.8 thousand joules.
I have a question concerning this energy plot.
Yes.
What is the realistic granularity on the time axis?
You mean the sampling?
Yeah.
I did 0.05 seconds as a sampling. And last thing is we added prefetching, so just a smaller optimization. Again, we have a small gain on performance on gigaflops, but on energy, I've seen a little bit. I've seen a little bit more energy than before, but it's slightly the same, let's say. And just to visualize the performance that we have almost 10 times speed up in terms of performance elapsed time megapoint or gigaflops. And in terms of energy, we divided by 7 the energy that we consumed in this particular case. So performance optimization also can lead to energy reduction for our applications. So that's it. Night landing is a bootable processor. It's simpler to use than Kernel, than CAN-C, sorry. It can have very good impact on codes that are limited by bandwidth, but of course we need to do a lot of work in terms of optimization, in terms of vectorization and parallelism in order to get the best of this architecture. And of course, in terms of setting, we need to figure out which setting is best for each application, which can be a little bit cumbersome for some clusters or for some installations.